Hello everyone. In this session, we're gonna learn about titration. That is acid-base titration. And here's some of the definition regarding titration. First one is what is titration? Titration is the process of adding a standard solution from burette to an analyte. The reaction is believed to completed. And next one is equivalence point. What is equivalence point? It is the point at which the process of amount of titrant is chemically equivalent to the amount of analyte in a sample. And what is endpoint? Endpoint is the point at which the indicator changes its color in the titration. And last one is indicator. Indicator is an auxiliary substance that changes color in response to a chemical change. And coming to acid-base titration. What is acid-base titration? It is the method of quantitative analysis to determine the concentration of an acid or base solution by neutralizing the unknown concentration of a solution with the known concentration of an acid or base. Basically, acid-base titrations are classified into 4 types. First one is strong acid and strong base. Second one is weak acid and strong base. Third one is weak base and strong acid. And last one is weak acid and weak base. And your first one is strong acid and strong base. Hydrochloric acid is reacted with sodium hydroxide to form a neutral solution. Is the example for strong acid and strong base. And there are 3 reasons in this titration curve. First one is before the equivalence point, and next one is at the equivalence point, and last one is after the equivalence point. And here, before the equivalence point, major constituents are HCl and NaOH, and major constituents at the equivalence point are NaCl, and major constituents after the equivalence point is NaOH and NaCl. And here in this graph, pH initially gradually increases, and when it reaches equivalence point, it increases rapidly, and behind the equivalence point, it increases slowly. And coming to next type, that is weak acid and strong base. Here acetic acid is treated with sodium hydroxide, is an example for weak acid and strong base. That is, here there are 4 reasons in this type of titration curve. First one is before the addition of any titrant, and next one is before the equivalence point, and next one is at the equivalence point, and last one is after the equivalence point. In this titration involves direct transfer of proton from weak acid to hydroxide ion, and here pH will increases rapidly, and next gradual increases when it reaches equivalence point. And next type is weak base and strong acid. Here acid and base will react to form an acidic solution. During this titration, conjugate base will be produced, and here pH is below 7 at the equivalence point. And last one is weak acid and weak base. Here acetic acid is treated with ammonia, is the example for weak acid and strong base. And here at the equivalence point, the pH is greater than or lesser than 7.
I'm going to explain about indicators and theory of indicators. These are the contents. First, we look into introduction. An indicator is a substance which helps to indicate the pH of a solution. An indicator changes color depending on the pH of the solution analyzed. Because of this, they are also known as pH indicators. Universal indicator is a very versatile as it can measure pH across the entire scale from 0 to 14. It is not a single indicator, but rather a combination of various indicators. If we look at this color changes of universal indicator according to the pH of a solution, it resembles a rainbow. If the universal indicator solution turns red color, it indicates a strongly acidic with a pH of 1 to 2. If the universal indicator changes color to green, it means that the solution is neutral with a pH 7. If the universal indicator solution turns dark blue or purple, it means that the solution is strongly alkaline with a pH. Universal indicator paper works in exactly the same manner. Litmus is the another indicator commonly found absorbed onto paper as litmus paper. Blue litmus paper turns red under acidic condition with a pH less than 7. Similarly, red litmus paper turns blue under alkaline condition with a pH 7. Phenolphthalein is an indicator commonly used to determine the endpoint of a strong acid, strong alkali, and similarly weak acid, strong alkali titration. It goes from colorless to pink at a pH 8.2. Similarly, methyl orange is used to determine the endpoint of either strong acid, strong alkali, similarly strong acid, weak alkali titration. It is red at a pH lower than 3.1 and yellow at a pH higher than 4.4. In conclusion, indicator or substances that change color at a certain pH. Point at which indicator changes color is known as the endpoint. Next, we'll look into theory of acid-base indicator. Two theories has been proposed. First one is Ostwald's theory. According to this theory, color change is due to ionization of acid-base indicator. The unionized form has a different color than the ionized form. This is the first theory which explains the behavior of indicator, and it is given by the W. Ostwald. The ionization of the indicator is largely affected in acids and bases as it is either a weak acid or a weak base. And the second is resonance theory. It is also known as quinonoid theory. The acid-base indicator exists in two tautomeric forms having different structures. Two forms are always in equilibrium. One form is termed as the benzenoid form and the other is termed as the quinonoid form. Action of phenolphthalein indicator. Phenolphthalein is a diprotic acid and is colorless. It dissociated first to a colorless form and then losing the second proton to an ion with a conjugated system, a pink color results. And the action of methyl orange indicator. It is another widely used indicator and it is a base and it is yellow in the molecular form. Addition of proton gives a cation which is red in color.
In this session, I am going to discuss about complexometric titration and precipitation titration. In complexometric titration, about introduction, EDTA titrations, titration curves, and some common indicators used. And in precipitation titration, about introduction, titration curves, Poisson's method, Pollard's method, and Morse method. First, let us know about complexometric titrations. It is a type of titrimetric analysis which involves formation of a soluble but slightly dissociated complex. For example, when silver ion reacts with cyanide ion, a stable complex is formed. In the above example, silver is the central metal atom and cyanide is the ligand. If the complex undergoes substitution reaction very rapidly, then the complex is said to be labile. These are some of the common complexes formed by complexometric titrations. To understand about the stability of complexes, let us consider an example. In these two reactions, K1 and K2 are called as stepwise formation constants. If we multiply both K1 and K2, then it is called as overall formation constant. Now let us know about EDTA titrations. EDTA contains fixed potential sites for bonding with metal ions and hence it is called as hexadentate ligand. It always forms 1:1 complexes. Titrations using EDTA as a titrant are called as EDTA titrations. EDTA is a remarkable titrant because it forms complexes with all cations. Complexes formed are very stable. This stable form of complex gives a large cage-like structure in which cation is effectively surrounded and isolated from solvent molecules. Now let's study about titration curves. Advantages of titration curves are to determine feasibility, to select proper indicator. Factors which affect titration curves are concentration of analyte and titrant and equilibrium constant. Indicators used in these titrations are metallochromic indicators. In metallochromic indicators, complexed and uncomplexed forms of indicators can be differentiated. Some of the common indicators used in these reactions are erichrome black tea and pattern readers indicator. Erichrome black tea is a triprotic acid. It is in the form of H3 ion. In aqueous solution, it dissociates into H2 ion form, which is in red color. When it is dissociated into H-ion2- form, it will be in blue color. When it is converted into ion3- form, it will be in yellowish orange color. This is the structure of pattern readers indicator. Complexometric titrations are commonly used in determination of calcium in limestone, determination of aluminum and magnesium in antacid tablets, in the determination of mercury in algicide. Now let's study about precipitation titration. It is a type of titrometric analysis which is based on the reactions that produces sparingly soluble substances. If AgNO3 is used as a titrant, then it is called as argentometric titration. Solubility product constant is denoted as KSP and it is the measure of completeness of reaction. The data required for construction of titration curves are calculated from concentration of analyte and titrant and solubility product constant. Now let's know about Morse method. In Morse method, there will be a formation of colored precipitate. It is developed for the determination of chloride, bromide, and cyanide ions. It uses AgNO3 as titrant and potassium chromate as indicator. This is the titration reaction and this is the indicator reaction. The molar solubility of Ag2CrO4 is nearly 5 times that of AgCl. As a result, AgCl precipitates first. Now let's know about Fazan's method. In Fazan's method, adsorption indicator will be used. For example, fluorescein, dichlorofluorescein, tetrabromofluorescein, etc. And in Wollard's method, we will perform a back titration and at the end point, a colored complex will be formed.
I'm speaking on conductometric titration. Conductometric titration is a process in which concentration of sample is determined, and it is done by adding a titrant of known concentration in measured volumes to the analyte. The instrument used for measurement of conductance is conductometer, as shown in the figure. Conductivity of an electrolyte solution is a measure of its ability to conduct electricity. The SI unit of conductivity is Siemens per meter. The electrodes used here is conductivity cell, and it is made of pyrex or quartz and are fitted with 2 platinum electrodes. KCl is used for calibration of conductivity meter because it is very stable. Types include strong acid and strong base. When HCl reacts with NaOH, NaCl and water is formed. H plus is replaced by Na plus and conductance decreases. After endpoint, conductance increase due to OH minus. Second one is strong acid and weak base. When HCl react with NH4OH, NH4Cl and water is formed. Before endpoint, H plus is replaced by NH4 plus and conductance decreases. After endpoint, conductance becomes constant due to common ion effect. Third one is weak acid and strong base. When acetic acid and sodium hydroxide reacts, sodium acetate and water is formed. Before endpoint, H plus is replaced by Na plus and conductance decreases. Then conductance increases due to sodium acetate. After endpoint, conductance increases due to OH minus. Let us move on to potentiometric titration. Potentiometry is a technique that is used in analytical chemistry, usually to find the concentration of a solute in solution. For most potentiometric measurements, either the saturated calomel reference electrode or the silver-silver chloride reference electrode are used. When the pair of electrodes are placed in the sample, solution or analyte, it shows the potential difference between two electrodes by the addition of the titrant or by the change in the concentration of ions. Commonly used for the determination of different organic and inorganic ions in various areas such as process control and environmental, industrial, agricultural analysis, and also medicinal drug analysis. What is the difference between iodometry and iodimetry? Iodometry is the quantitative analysis of a solution of an oxidizing agent by adding an iodide to form iodine. Iodimetry is a volumetric analysis involving either titration with a standardized solution of iodine. Let us take one example. Determination of arsenic in ant control preparation by iodimetry. Arsenic 3 present in ant control preparation can be determined by titrimetry, that is iodimetry, using iodine as titrant and starch as indicator. Procedure include weigh approximately 1 gram of ant control powder into beaker, dissolve in 10 ml of 20% NaOH, neutralize by adding concentrated HCl using phenolphthalein indicator, then add 1 gram of NaHCO3, dissolve, make up the solution to 100 ml with water in a volumetric flask, mix and use. From this, transfer 10 ml of ant control preparation into conical flask, add 20 ml H2O, 2 gram NaHCO3 and 1 ml starch indicator. Titrate with 0.01 normal iodine solution. And this can be calculated using the formula 1 ml 1 normal iodine is equal to 74.9 mg of arsenic.